My name is Carlo Manfredini. I'm R&D Director for Emona TIMS, and I would like to give you a quick overview of our product range and our methodology and a demonstration of our remote access labs. So we'll just quickly go through a PDF giving you an overview. So Emona TIMS, we've been manufacturing for 30 years now and supplying to universities all around the world. We are based in Sydney, Australia, and we have over 150 universities in the States that use our equipment, and in more than 50 countries. Our teaching philosophy is that whilst technology changes, principles remain the same. And so what we do is we endeavour to make equipment that teaches the principles behind telecommunications and electronics theory, and not just operating equipment or the technological aspects of that, which can change over time, as you can see here. As far as the remote access labs goes, in 1999, we developed a remote access version of our telecommunications product, TIMS, which you can see down here on the left. It is a system which has a number of modules which are patched together. And by adding a server unit to this and a multiplexer, we are able to share this unit amongst many students. 30 or 40 students at a time can use the experiment because the requests to the unit are queued by the server, and the screenshots are sent back to the student according to their requests. So when a student isn't requesting the unit, there's no waste of the server. It's available to service somebody else. So it's time shared, but not in terms of blocks, just in terms of requests. So simultaneous use of the experiment to multiple students at the same time. And now, today I'll be demonstrating our netCIRCUITlabs product, which is once again, a physical box which is connected to your LAN, and it has application boards which plug into this box, and each one of those application boards is a complete lab of experiments. And before I go any further, let me show you what that looks like physically. As you can see, it is a single box, and it has an application board plugged into it. The application board simply connects into the top of the unit, and this particular board delivers 15 OpAmp circuits. With the same unit, you can have a different application board. Simply place the unit on top. The unit will auto-detect what board is plugged in, and if the student goes to the IP address, they will immediately be able to access these experiments. So why do these remote access needs arise? Well, as we move into a blended learning environment where we have on-campus and off-campus learning, as you know, lectures can be delivered via video. And simulation is available on campus and off campus. However, hardware labs are very difficult to deliver remotely, and yet there's a need for engineering students to do hardware labs with real hardware, not just simulation. So we provide these products which allow remote access to real hardware labs. And I should say, just coming back to this, these labs are not designed to replace the on-campus labs. These are a complement, in the same way that all off-campus learning is a complement to your on-campus learning. Students will be much more productive and learn more effectively if they're able to work at their own pace away from campus. So let's have a quick look at these. At this product range. So the netCIRCUITlabs is this box. It sits in the lab, connected to your LAN at a particular IP address of your choosing, has an application board on it, and students at home or in class, anywhere, on their tablets, on their browsers, can access this unit. There is no software download. It's a straight browser access. One unit, many students at the same time. What's the benefit? Obviously, many students at the same time accessing your lab 24/7, 365 days a year, saves costs, saves storage, saves inventory, lab technician time, increases lab access, supplied ready to use. So no setup and no maintenance. So remote control of experiments. We have the experiment platform sitting on the box, connects to the LAN and can service multiple clients, which are your multiple students, either on a LAN or across the internet. The interface is very intuitive. We have modules like a function generator, fully featured function generator. We have switches which you can click. We have potentiometers which you can vary by dragging your mouse. We have knobs which you turn. So it's very intuitive. It's just like the real thing. We have an oscilloscope, which is a 4-channel oscilloscope. We have a spectrum analysis, X, Y mode, cumulative mode, and of course you have the ability to capture screenshots, etc., etc. So that is the netCIRCUITlabs product. So now let us look at physically what it looks like. Now downstairs here in the office, I have 4 of these units set up, which you can access yourself for demonstration purposes. Each one of these boxes has a different application board on it, and so it's serving out a different set of labs. You can just have one of these boxes and multiple boards and swap them as you see fit, or you can have multiple units. We happen to have multiple units, so we can deliver 4 different sets of labs at the same time. So here are the IP addresses, and I'll put a listing of that up later on when I do a demonstration. So the first board we'll be looking at is the OpAmps board. Here are some typical screenshots of what you'll get from each experiment. Everything we create is well documented, step-by-step instructions, some theory, and it is designed to complement your lecture material, not replace your lecture material. The second application board we make is the analog transistor trainer. There's a number of circuits here. Once again, you can see the schematic is displayed on the screen. The student is able to click and move around and vary and explore that real circuit. Something I should say, as well as exploring the circuit, they can also run a simulation alongside this, package and compare the two together. The third product is a digital logic board where we have many digital logic functions implemented. These are implemented inside an FPGA, and the student makes connections of all these different logic gates. And so instead of having this typical arrangement, which whilst it's fun and for the student is very time consuming and prone to error, we have this situation where the student can identify the gates they want, make the connections themselves, and then these connections are actually real physical connections inside the FPGA itself, fully dependent and controlled by the student. You place the gates that you want, you make the connections you want, and you have an unlimited amount of experiments possible. Finally, the fourth product is a breadboard product, where we have a breadboard. You make your own circuits and you connect them to our remote control pots and our remote control switches, and our server delivers your specific circuits to your users. So for example, online at the moment, I have some simple RC circuits connected to our switches, and I have a triangle wave generator connected to our potentiometers. Here's the control panel where you can see the resistors, the switches, and the scope points that are available for you to allocate to your own circuits. So you can deliver your own circuits remotely to your students. These circuits could be anything. It's up to you. So that's the end of my PDF. Now we will open up the browser and have a look at some experiments. So let's pop open the browser. Okay, so here on the right, you can see the IP addresses I'm going to be using for this demonstration. The top 5 are available all the time for you to access. The bottom one is a beta address at the moment. It will also be shifting, but for now it is at a different location. So let's look at the first box that I showed you in that picture, the 111. So we go to this IP address, and you can do this yourself. Enter. User. Visitor. Submit. Okay, so this box implements digital logic. So let's have a look. Here we have some logic gates to choose from. Let's put down a binary counter. Let's use the scope to look at the signals from that binary counter. Okay, let's shift the scope around. Let's change the time base. Now let us put down another gate. Exclusive OR is interesting. Let's connect that. So as I click, these connections are being implemented in the real physical hardware, albeit inside the FPGA. Okay, so now we have the exclusive OR of those two signals presented on this cable here. So as you can see, it's possible to load more complex circuits, which are pre-wired. So you as the instructor can create your own circuits and deliver them to the students, make them public. You can load finite state machines, much more complex circuits. You can move the cables out of the way if they're in the way, just by dropping and dragging. And you can have a blank slate. Now, as an interesting example to show that this is real physical hardware, let me select an inverter and let me connect the output to the input of that inverter. And now let's look at what the output of that inverter is doing. As you would expect, connecting the output of an inverter to the input of an inverter will cause oscillation. And in fact, it does. And if we go right down to 1 microsecond for division, you can see that this circuit, this gate, is actually oscillating at 6 megahertz. So just showing you that this is real physical hardware, not some kind of simulation. Students have real control over what they're looking at. Okay, so that's digital logic. Let's move on to the next application. You would just grab a different board and plug it into your unit. In this case, it is the transistor circuits board. Okay, so first circuit that presents itself is this amplifier. We can select from other ones. We have a feedback amplifier. We have a differential amplifier. Now, these circuits are fixed generally, but there are switches that you can change. There are signals that you can vary, input signals. You can change the amplitude on these input signals quickly and easily. You can vary the potentiometers to change the performance of the signals, change the switches, and so on. And this can all be done by each student independently and individually because the unit is sharing itself upon request. So if you look down here on the left, you have number of users. At the moment, I'm the only person using this, but there could be 10, 20, 2, 3 users at any one time. If we go to the next lab, we have our OpAmp circuits. User, visitor. Okay, here we have a number of circuits available to choose from, and these circuits are implemented on this board here downstairs. If I go to, for example, duty cycle, variable duty cycle, there you can see it's already wired up to show me a few points. Let's move these things around a little bit. Let's look at a different point. Let's move my blue point to this point. I can make that change. Now I'm going to vary the potentiometer. I'm going to drop, click, and drag the potentiometer. As you can see, the circuit's changing. We don't have measurements here. Students need to click and take all their measurements off the scope. They can measure using our cursors. They also have access to frequency response. They can look at the frequency response of signals. They can capture the signals, etc., etc. So look, that is the OpAmp circuit. There's quite a large range of circuits to choose from. The next board is the 555. This is the breadboard. Once again, log in. You can do this at home anytime. Okay, now here we have the control panel for that circuit, which I've implemented. Now, on the control panel, I can do something like, I'll change the time base to maybe 200 milliseconds. Now I'm going to get this potentiometer and drag it. Because this is variable and can be changed on a day-by-day basis, you need to let the students know what circuit it is that they're implementing. So what we have down here is we have a button, Experiment Overview. When I click that button, it will open a PDF which you have loaded into the server yourself. So you create a PDF with information about the schematic. In this case, this is the default. This is the default page, and the student will be able to have that in a window. Alongside the control panel, so they know what they can access. Here, they know what they can access because the signals are lit up. They can flick switches, etc. I don't know off the top of my head what circuit is implemented here, but it is basically those RCs and those generators that I spoke of before. This could be your own circuit delivered remotely. And so, look, finally we have another system which we call netTIMS FreeWire. Now this is where we can deliver telecommunications teaching, which looks exactly the same as our modular approach, our premium product of individual modules, except that the modules are all inside one of these units, and you can access it and make all the connections yourself remotely, multiple students at the same time. So just imagine your entire lab class could be accessing telecommunications labs, 30 or 40 experiments at the same time from one unit, just sitting in the corner on a LAN. So here is the same format. As you can see, we have a number of empty slots. We have our instrumentation down the bottom. So let us look at the menu to choose from. Let us look at, here is the menu, adders, amplifiers, exclusive OR, function generators. Let's put a function generator down. Let's look at that signal. Okay, I've made a connection. I'm going to change the amplitude. Okay, and there you can see it takes about 1 to 2 seconds, and my request to the server has sent me back the signal that is coming from the hardware. Now I'm going to put down what I call master signals, which is where we have our standard oscillators, and I'm going to put down an adder. Now I'm going to take my sinusoid into the adder. I'm going to look at that with my B channel and increase the amplitude. Okay, so there's my 2 kilohertz signal. Now I'm going to change my function generator to DC, and I'm going to connect it to the adder, and I'm going to increase the gain on my DC, and I'm going to change the DC value from 0 to something bigger than that. So here you can see I now have a DC value, and you can see that the blue signal, the output went down. So, okay, my output went down, my DC level went up. Okay, you can see that changing. So now I'm about to do amplitude modulation. So now I'll put down a multiplier. Multiply, we have 4 multipliers. So I'm going to multiply that message with a carrier. 100 kilohertz carrier, and I'll look at that on the D channel. Okay, and you can see there's some terrible aliasing there, as you would expect from a scope. So I'll change the time base. Okay, change the time base to a more appropriate time base, and then you can see we have some amplitude modulation, which I am controlling in real time. There we have like 100% modulation approximately. Students would take measurements, period, amplitude. They could look at the spectrum. There's the spectrum as you would expect. Now you can see the carrier and the two sidebands at 2 kilohertz. Let's put in a slightly more interesting message. Let's select a VCO. Here's a VCO. As I do this, I'm actually selecting real physical modules, and we will replace that. We'll take the output of the VCO and put it into the adder. Now you can see I have an inappropriate frequency, so I'll switch to low, and then I'll vary my frequency. And as I vary my frequency, you can see the AM change, and you can see the sidebands change. I could switch off the time base, I could switch off the frequency. Okay, so look, quickly and easily, you can see that I've selected 1, 2, 3, 4, 5 physical modules, which are mathematical functions, and I patched them together. These are real physical hardware connections, and we implement these physical connections using a massive analog cross-point switch inside this unit. So when you have free wire in your lab, you have a suite of analog and digital blocks. You have a massive cross-point switch and a 4-channel scope, which allows you to deliver multiple experiments to your students. These can be saved locally or privately, and they can be delivered to students. Students can pull up the experiment that you have made for them and explore it, or they can create the experiments themselves over time. So that is a quick introduction to our product suite. And you can find out about this at netCIRCUITlabs.com. Thanks very much for your interest.